Lesson 3, Linear Programming Setup. The learning intention for today is that students will understand how to convert real-world scenarios to linear equalities and use them to set up what we call a linear programming problem. The success criteria: if you can identify decision variables and interpret constraints into linear inequalities from a variety of real-world applications, well, then you've understood what we're talking about here. So there are some strange terms there, so let's start with some vocabulary. First of all, what is linear programming? Well, quite simply, it's the process of using linear inequalities to solve real-world problems. Often what we're going to be doing is we're going to be looking for a maximum or a minimum solution. That's also called an optimal solution. So these types of problems are also sometimes called linear optimization. Decision variables. So these are the unknown values that we're looking for. So a variable, of course, is something that we don't know, and we're trying to figure out, all right, what are we trying to learn here? Those are our decision variables. We will have two. There'll be x and y, but in theory and in practice, there's no reason you can't have 3 or 4 or 5 or more decision variables. We just don't cover that in this course. And then we have constraints, which are restrictions on the decision variables. So for example, our variables must be positive, or the sum of them must be less than 8, or we'll see lots of different examples of what that could be. Because again, the decision variables are real world things, like maybe we're looking at the number of cookies. Well, it doesn't make sense to have a negative number, so we'll have a constraint that says that the number of cookies must be greater than or equal to 0. Each of these constraints will be translated to a linear equality. So x is greater than or equal to 0, x plus y is less than 8, whatever it might be. We're translating from English to mathematics. And all of the constraints will have more than one, will have lots of different restrictions. Together they form a system of linear inequalities with a feasible or required region. So just as we did in lesson 2, we'll graph all of these linear inequalities and get the solution region for the problem. Lastly, we have what's called the objective function. We're not going to focus on that too much today. That will be lesson 4, but that gives us a little bit more information about how we decide which one of the solutions within our feasible region, which point in that region is the best. So the steps, and again, we're not going to worry about objective functions today. First thing to do is identify the decision variables. These are the unknown values you're trying to find. So how do we figure out what variable is it? Is it the number of boys and the number of girls? Is it the price of cookies versus the price of sandwiches? What are the unknowns that we're looking for? We'll call one of them x and one of them y, as there are 2 of them. Next up is identifying the constraints. And this can be a bit of a challenge, but you really just have to practice and get familiar with the type of language. Those are restrictions on the decision variables, as I said before. Each one becomes an inequality. And some key constraints that we sometimes have are x and y greater than or equal to 0. Most often we will use, in linear programming problems, we'll have greater than or equal to. So don't forget to include those those constraints if the context of the question allows for it. And then graph all the constraints and identify and label the feasible region. That's all a little bit complex, so for the rest of this video, we're actually going to go through step by step an example, in addition to the other example videos that I create. So the example: Tempus Mathematics wants to sell their videos to an educational software distributor. They make 2 different types of videos: lesson videos and example videos. The table below shows the amount of time it takes to do the various different steps in the videos, as well as the maximum total amount of time that can be spent on each step in a week. They want to do an analysis on how many videos can be made each week. So let's analyze this little table here. So we've got our two types of videos. We've got lesson videos and we've got example videos. And there's three stages that are made, or three stages that are a part of designing these videos. There's planning them, filming them, and lastly, editing them. And there's an amount of time, all of these are in hours, that it takes to do each one of these. So for example, a lesson video takes 3 hours to plan, whereas an example video only takes 1 hour to plan. And so on, filming a lesson video takes an hour, filming an example video takes 2, and a lesson video takes 2 hours to edit, whereas an example video only takes an hour. And over the course of the week, in amongst our busy schedules, we've set aside no more than 10 hours for planning, 8 hours for filming, and 7 hours for editing. We may not use all of that time, but that's what's available. I can't spend any more than 8 hours filming because, I don't know, maybe my voice gets tired after that. So the first thing to do is to identify and determine the decision variables and the constraints, sketch the feasible region. So step 1, what are the decision variables? So what are the things that I'm trying to figure out here in this analysis? Give you a moment to think about that. Well, there's two things that I'm trying to understand here. I'm trying to figure out how many videos of each type I can make. So I've got the number of lesson videos made in a week, which I'll call X, and the number of example videos, which I'll call Y. You could have done it the other way around, but for now, we'll refer to that, the lesson videos as X, and the number of examples as Y. Second step is to state the constraints. So what are the restrictions on the number of videos that I can make? Those restrictions, because we've got information about the amount of time, that's the amount of time spent on each stage. So I know for planning, I have to spend less than or equal to 10 hours, for filming 8, and for editing 7. So I should have a restriction or a constraint for 1, 2, 3 stages of making the video. So let's work our way through this. Restrictions on timing for each stage, 3 constraints total. Just said that, so we'll start with planning. So the total time has to be less than or equal to 10 hours. So already here I'm seeing an inequality symbol. Something is less than or equal to 10 hours. The total planning time. I need to figure out how to build in my X and my Y. So lesson videos, those take 3 hours for every video. So if I film one lesson video, if I plan one lesson video, that takes 3 hours. If I plan 2 lesson videos, that's 6 hours, and so on. Examples are 1 hour per video. So the total amount of time that I spend on lessons is 3x hours. Because again, if x is 1, that's 3 hours spent planning. If x is 2, that's 6. If x is 3, that's 9, and so on. And the time on examples is y hours. 1 hour on every one. So if I plan 10 example videos, that's 10 hours. It's just y. But it's the total time that has to be less than or equal to 10. So my constraint is the total time here, which is 3x plus y, is less than or equal to 10. So this is my first constraint. Next up, we'll do, this should say, filming, a restriction on the number of hours spent filming. have a go at creating that yourself. So the process is very similar. The total time now is less than or equal to 8 hours rather than 10. Lessons, which again, remember, is X, is 1 hour per video. Examples, Y, are 2 hours per video. So the total time spent on lessons is X. The total time spent on examples is 2Y, 2 hours for every example. So my constraint, the total time is X plus 2Y, has to be less than or equal to 8. That's our next constraint. And there's one more. I'll let you just read through that quickly, get down to our final constraint, 2x plus y less than or equal to 7. Again, very similar process to the last one. Okay, so now we want to look at graphing our constraints. So what are they? We've got this one, which was the planning. We've got the filming. We've got the editing. And stop and think for a moment if there are any other constraints. Well, there are. It doesn't make sense to have a negative number of videos. So for that reason, X is going to be greater than 0 and Y is greater than or equal to 0. It's possible that I don't make any lesson videos, but I can't make -1. Because of these constraints here, I can restrict my graph to just quadrant 1, the positive X and positive Y axes. So I don't have to graph those anymore. I know that already my feasible region is going to be within here. I don't have to worry about whatever's out here. So the first one, we graph 3x plus y less than or equal to 10. Shaded that in. Graph the next two. Because again, we've dealt with that one, dealt with that one, dealt with that one. Try and graph the next two on your own. Second one, in green here, x plus 2y less than or equal to 8. And the final one, 2x plus y is less than or equal to 7. Of course, I've got my x and y both greater than or equal to 0. So our feasible region, we can zoom in a little bit here. I'll just go back so you can see exactly what I've done. The feasible region is just in here. This little area in here, that's the area that has all 5 inequalities satisfied. It's colored blue and red and green. So just in here. Zoom that in, see it a little bit better. So following along basically the path around the outside here, this is my feasible region, which I will label. And of course, as I've said this before, when you're dealing with colors, sometimes it can be a little bit difficult to do this by hand. So another way of showing it is just like this. So I've drawn the shape of something like that, and that is my feasible region. I've now got 2 other examples. Have a go at creating and the constraints and sketching the inequalities for each of these. Example 1 and example 2, and then we'll finish up. So you will have been successful if you can identify decision variables and interpret constraints for a variety of real-world applications.